Hi, in this video, let's talk about database replication. Why database replication? Database replication is a very important concept in distributed systems. The reason why we want to replicate database is because if one copy of the database goes down, the whole application will fail because the application can no longer get access to data. So we want to replicate database into several different copies. And this is very challenging because replicating database presents several complex technical challenges, such as how do you keep the database in consensus, and how do you keep the database synchronized, and how do you replicate data across the databases without introducing too much lag. The motivation behind replication is we want to keep our system highly available and fault tolerant so that if one of the replica goes down, we can still have access to the database. We begin by talking about the formal definition of what replication is. Replication is the idea that we want to keep the same data on separate machines connected through some network. In our introduction to replication, we are going to make a key assumption, and that we assume the database is, the data set is small enough to fit on one machine. And so if we're distributing if we have a distributed database, let's say we have 3 replicas, each replica can contain a complete set of the entire data sets, right? So if you look at this diagram, we have 3 databases, three replicas. Each replica should be able to contain all of the data available. Okay. There are 3 kinds of strategies in database replication. The first strategy is the single leader strategy. The second strategy is the multi-leader, and the third one is leaderless. In this video, we will talk about single leader in detail, how to set up a single leader cluster, how does it work, how do we keep the followers consistent with the leader, and what are the failure conditions. And let's begin by talking about the configuration. So in a single leader setup, here we have a database cluster, right? I draw the cluster in a rectangle box. All of the 3 copies, all 3 copies have the same data. In the single leader configuration, there is, as the title suggests, there's a single leader, right? So this one is the leader. Let me switch the color. And the leader passes replication streams down to the follower. So we have a replication stream down to the followers. So any modification done to shard A, our leader, is replicated to B and C. So if we have a client here who wants to access this database, a key characteristic of a single leader cluster is that the leader can perform both read and write. Okay, so this one, leader can process read and write. This is very important. And replicas, which is B and C, our followers, can process only read. So B and C processes only read, and the leader can process both read and write. So in this configuration, this is very good for heavy read traffic, right? Because we can essentially do 3-to-1 read to write. because we have 3 shards that can handle reads and only 1 shard that can handle write. So the single leader is great for heavy read traffic applications. Right. And let's talk about synchronous versus asynchronous replication strategies. So what is synchronous and asynchronous? Okay. So synchronous and asynchronous is how we define our replication clusters, replication strategy for our cluster. So in this example, we have a client who is trying to write x equal to 5. Right. So at this time, our client is trying to write x equal to 5. This write request gets passed down to our reader node A. This is our leader. Right. Initially x equal to 1. The leader receives this write request, and as we discussed earlier, the leader needs to pass this write request also to its followers. So I draw this slanted line because there's some network latency in between. Right. So in this configuration, we defined B to use synchronized replica. Okay. And C, we defined it to use asynchronous replication, right? So what does that mean? Well, when B receives the write request, it takes some time to push to the database, right? To push to the database. Let's say it takes this much time. And once it's done, it says, okay, it's completed. And it sends the response back to the leader. And let's say the leader receives the OK response somewhere here, right? And the leader itself has also completed this write request, okay? And it took this much time. Synchronous tells the cluster, and tells the application developer that this cluster needs to wait for its follower to also commit that value before saying that this value is committed. So here, once both A and B are completed, then it sends that response back to OK, sends the OK response back to the client, right? And so when the client tries to now read X, if the read request lands on either the leader or shard B or node B, we're going to see X as equal to 5. Okay. And going down here, if C is asynchronous, in the asynchronous configuration, the leader does not wait for C to respond. So leader waits for B, but not C, because C is asynchronous and B is synchronous. So that's the difference, right? In the synchronous configuration, leader will wait, and in the asynchronous, leader will not wait. Okay. So you can see what the consequences here are. Let's say if read X, right? If read X lands instead of on A and B, it lands on C. Okay. And C has not yet finished updating, right? C finishes updating here, right? It then tells A that it's finished. It then tells A that it's finished, right? So if the read requests land in between this timeline here, the client is actually going to see X as equal to 1 because the update hasn't completed. And that's the consequence of using asynchronous, is that asynchronous allows faster response, faster latency, but we could read stale data, right? On the contrary, Synchronous is slower, but we have guarantees. Typically in our database, modern databases, we enable what's called semi-sync. Semi-sync means that, let's say you have 5 nodes, only 1 or 2 of them are synchronous. The rest are asynchronous. So that's semi-sync. Hope that makes sense. Now let's talk about adding a new follower. Okay, we again have this database cluster. Okay, A is the leader, and we have existing B and C, and we want to add a new node D. Okay, and D is a follower. So what do we need to do? So there's 3 steps when it comes to adding a new follower. The first step is we want to create a snapshot of the leader from the transaction ID. The leader maintains a replication log. Okay, each replication log, each segment of the replication log has a TXID. Let's say this is TXID 0, and this is TXID 1, this is TXID 2, and this is TXID 3. We want to take a snapshot. Well, what is a snapshot? A snapshot is what the database looked like at any given point in time. So right now, our database has the following 3 keys, right? It's got account 1, account B, and account C. And we take a snapshot at this time where TXID is equal to 104. Let's say instead of 3, this is 104, right? And so account A is equal to 400, account B is equal to 200, and account C is equal to 1000. The point-in-time snapshot, the consistent snapshot, contains all of the key value of the database at that given time, right? And we pass in, we make a note of the TXID. In this case, the TXID is 104. So we know that all of the TXID before 104 should already be in the snapshot. And all of the TXID after 104, 105, 106, 107, etc. These are not yet, these are not in the snapshot, right? This is in the future, right? This is our future modification. And the reason why we have to do it this way is because as we're adding a new node into our cluster, our user could be updating, right? Could be sending additional updates to our database. We don't want to lock the database down and freeze all of the values and all of the tables just so we can add a new replica, right? We would lose availability if we do that. So we do it by creating a snapshot, and we tell D that, hey, this snapshot contains everything up to TXID 104. So snapshot and TXID 104. Everything after TXID 104 needs to be replicated. Okay. So in step 2, node D copies the snapshot. Okay, copies everything in the snapshot over and makes a follower, right? And once the copy is completed, it knows that we're at TXID 104, and it's going to maintain a replication channel. So replication channel, or we call it replication stream. And it's going to stream everything from 104 to, say in this case, 104, 107, so 107. And once the replication is completed, we then say, okay, D is online and ready to be used. So You can see as an example here, right? Yeah, and let's go to the next section. So failure mode. What happens if a node goes down? There are two types of failure modes that we could experience in this single leader configuration. If the follower fails, that's okay. We have the leader set up. This one's easy. Let's just bring up a new follower from what we defined above, from above. If a leader fails, we would have to elect a new leader, right? So let's say if the leader fails, let's say if this one fails, one of these, B, C, and D, they need to elect a new leader. So let's say if we elect B as our new leader, anything that A was processing, all of A's write will be lost. If it's asynchronous, right? Because as we looked at it here, if any of these have asynchronous writes and our leader goes offline, all of these requests will be lost. Okay. So this is the downside of using, this is the downside if we need to elect a new leader. The other downside is that there's a potential case where we have a complete network fault, right? So let's say if B, C, and D, they stopped communicating with each other, right? Or let's say B and C are still communicating, but C is now isolated, right? There's a network fault between the three nodes, okay? What will happen is now B is going to be the new leader. Let's say B is new leader, and in this isolated environment here, C is also the new leader, and we'll end up in a situation called split brain. I hope this video helped, and we will continue discussing these topics in the next video.